So my apologies for the delay. I accidentally left the call while I wanted to unmute my microphone. So yeah, because the buttons, I don't know, looked a bit similar to me somehow. Dirk, I don't know whether you want to record a discussion.
I already am recording, so.
Oh yeah, that's what I thought, because that just.
If it's not relevant, I will cut it. But
yeah.
All
right, let's start with these questions. Can you detect extracellular vesicles smaller than the resolution R with optical microscopy? Please motivate. So for the discussion, please, if you want to contribute, unmute your microphone and please let me know your answers and opinions on this.
Okay, I think that you can. I think you can detect their existence, just like when a faraway exoplanet orbits in front of its star. The light will change, but I don't think you can really determine exactly what kind of vesicle it is.
All right. Yeah, that's exactly how it is. I find the analogy to detecting stars very nice. I mean, from the size of a star, if you would look with a telescope to the stars, at least to the size of the image, from the size of the image, you cannot derive much conclusions. But from the brightness and other properties, you can. I'm not an astronomer, and it's the same here. And I think the best example was on the slides. So if we go to nanoparticle tracking analysis, the schematic of this setup, it's basically the same as a microscope. Yeah, maybe the laser goes perpendicularly, is perpendicularly placed with regard to the detection and the camera. But for the rest, it's basically a microscope. And these particles are sub-resolution limit for sure, because we size them based on their Brownian motion. These were most of them between 100 and 200 nanometers. So yeah, you can pick up their scattering signal, but the size of the image does not contain information about the size of the object. But the brightness and the diffusion speed do. Yeah. That was a tricky question because, you can in fact measure signals with a normal microscope of objects that are below the resolution R of the microscope. Only you have to be careful with interpreting these data. All right, very nice. Question 2. Check the specifications of this nanoparticle tracking analyzer. I don't know whether you did, but if you did, can you detect, in fact, vesicles with a diameter of 10 nanometers with this instrument? Why or why not?
Yeah, you should be able to. Because
Why?
The specs on the site say that it's usable for, let me see, all types of nanoparticles from 0.01 to 1 micrometer. And 10 nanometers is 0.01 micrometer, so it's just about right then.
So how about this asterisk, which is placed there?
Sample and system configuration dependent. Okay.
So how about the sample? Yeah, the configuration is as it is. Let's say you get really this nanosite NS300 with the best camera. How about the sample? So where does it get tricky here? Anybody, any idea?
Or maybe if you label it with a fluorescent antibody, that makes a difference.
Yeah, that's it's nice. It's possible with this technology to label your particles with some fluorescent tag. For example, an antibody, fluorescently labeled antibody. It would change the detection limit. It's not that easy with this instrument. The main reason is, and I will just give you some background information of this instrument and fluorescent labeling. The main reason is that you want to track your particles for at least several seconds. So you have seen this movie here on the screen. These particles are, actually, is it playing? No. See, these particles are moving, and if you track them for several seconds, you can determine their diameter. Now, most fluorescent labels actually would bleach if you would illuminate them with this high intensity laser. So you cannot track them several seconds because the fluorescent dye just damages after about half a second or something. So the combination nanoparticle tracking analysis and fluorescence is far from perfect. I bet they don't write that on this website, but it's not an ideal combination. Only with quantum dots, which do not suffer bleaching so much, some do little, but yeah, you can do it, but it's very difficult to label, for example, vesicles via an antibody to quantum dots. This chemistry is very difficult. So, no, okay, let's consider light scattering. Let's consider light scattering only. What does this asterisk mean in terms of light scattering? The manufacturer writes, okay, you can detect all nanoparticles between 10 nanometer up to 1 micrometer. You can size them, but this is sample dependent. So we want to measure vesicles. So can we measure 10 nanometer vesicles, and why not? Any more ideas? So if we just assume that our vesicles are solid spheres, so on which two properties of this sphere does light scattering depend on?
The radius.
Sorry, flat?
The radius of the spheres.
Exactly, the radius. That's very good. So about the radius, they make claims, right, on the website, because they say radius 5 nanometer you could detect, which is diameter 10 nanometers. Which other property?
Scattering coefficient.
The scattering coefficient. The scattering coefficient is a property of multiple particles in solution. So we are talking about one particle now. So you're close with what would be this property? It's an intrinsic property of the particle. You have heard it before, the term, for sure.
Maybe the cross-sectional area, which is related to the radius.
Exactly. The physical cross-sectional area is, of course, very closely is just one-to-one related to the diameter. Oh no, yeah, to the square, but
Maybe the density.
The density.
Yeah.
Yeah, the density. That's very close. But would that be the, let's say, the mass density or a different type of density?
No, the volumetric density, like how many EVs we have in a volume.
That's the concentration.
Oh, yeah, okay.
That's called number concentration. But now we're talking about one vesicle. We want to detect only one, and want to know what is the smallest single vesicle we can detect. So it should be independent of the concentration. All right. You're all very close. The answer number density. Yeah. That's if you look it up on Wiki, you have many different terms. It's a number density or concentration or particle concentration, particle number concentration. Sorry for that confusion. So the term I was looking for, and that's the intrinsic, one of the two intrinsic properties of a particle, a spherical particle, which are very important to calculating and determining their light scattering properties, are the diameter and the refractive index of the particle. So, and refractive index you can see as perhaps an optical density, but it's for sure not the real density of a particle. For example, if you take an oil, oil often floats on water, so it has a lower mass density, volumetric density than water, but it has a higher refractive index. So they are for sure not one-to-one related. All right, so it's the refractive index. Now, going back to the question, this website of NanoSite of Malvern shows this asterisk. And now the question is, what is the refractive index of a vesicle, and does this 10 nanometer apply to a vesicle? So what do you think? Any ideas on this? Is this manufacturing tricking you or not?
Well, maybe a little.
A little. Let's just take some plastic material. Polystyrene is used a lot to make nanoparticles. You can buy calibration particles of polystyrene. In Dutch, the material name would be piepschuim, probably, of polystyrene. Polystyrene has a refractive index of 1.6 at visible wavelengths, roughly. Any idea what's the refractive index of water? Yeah, but in the end, it's about the contrast in refractive index. What's the refractive index of water?
Was it like 1.1? Something like that?
No, one was air that we discussed before. Polystyrene, I will write it down just like in the classroom. No, 1.1 is too low. No, well, water, it's rather, it depends a little bit on the wavelength, of course, but at visible wavelength, you can fairly state 1.33. Yeah, like C. Vaira. Thank you. Now, the contrast between polystyrene and water seems low, but it's fairly high actually, and that causes the light to scatter. Now, if you take an EV, the refractive index is the highest which we measured, 1.40. So this seems pretty close to 1.6 or 1.33. But it makes that EV scatter light much less efficient compared to polystyrene. More than a factor of 10 less efficient. So the manufacturer here claims to detect 10 nanometer particles, and they demonstrated that by taking gold nanoparticles. Now, gold has a very high refractive index, because gold has such a high refractive index, it scatters light very efficiently, and you can just track 10 nanometer gold particles with this instrument. EVs, as you have seen here, have a much lower refractive index. If you want to know more about it, here we make some claims about that, and we derive for vesicles what is their smallest detectable diameter for this very instrument. And then, due to this large differences in optical properties, nanoparticle tracking analysis could detect only vesicles down to 70 to 90 nanometers. So there's a huge difference. So if you would buy this instrument and if you think you can detect 10 nanometer EVs, you're misled because due to refractive index differences and I think a little bit bold claims of the manufacturer, the actual detection limit in terms of the diameter of vesicles is much larger, rather 70 to 90 nanometers. So this is how manufacturers mislead technicians in the lab. Question 3. Surprising or not? Did you expect this? Normally the people shout no, but I suppose you do this with a muted microphone. Question 3. What would be your favorite technology for developing an EV-based liquid biopsy? Please motivate. Any thoughts? What would you choose to continue your research on vesicles? There's no bad answer.
I had nanoparticle tracking analysis. Oh no, sorry, flow cytometry. That was the one.
All right.
The last one you explained, if I'm correct, since you were very positive about it. It was incredibly fast, like thousands of particles per second, and they have to be hydrodynamically focused. So for a liquid biopsy, to me that sounds pretty good. I think transmission electron microscopy would not work because of the because you needed to get vacuum and absolutely no water inside and that kind of stuff.
All right. Very nice to hear your thoughts. Thank you. I am indeed a fan of flow cytometry that developed over the years. The first few years I didn't know yet. But the main reason indeed is that it's so fast. We can now, we can draw blood from a patient, add antibodies, and measure directly in the whole blood without even removing the cells with flow cytometry, the vesicles. In practice, we hardly ever do this. The main reason is if we take blood from patients or healthy volunteers, usually have no time to directly measure it because then our instruments are already used for some other investigation. So we do remove the cells with the centrifuge and we freeze the plasma. So just to remind you, the plasma was this yellow, watery a solution on top of all the cells if you put it in the centrifuge. So that we freeze, then we thaw it later on the same day for all the patients. We add antibody labels and we measure these samples with flow cytometry to analyze the vesicles. And we just start doing large studies since a year or two. So it's getting very interesting. All right. Sorry for being enthusiastic about flow cytometry because maybe that revealed already something. Any more thoughts? Who had a different technology than flow cytometry? No one. All right. Any idea what are the smallest vesicles which you can detect with a flow cytometer? So what would be the limit of flow cytometry? No thoughts? Now, that's no problem because we will figure it out for a commercial clinical flow cytometer during this lecture. So that was the short assignment. Let's move forward to single particle light scattering. And the first question I'm going to ask you, so if you have something to say, please unmute your microphone. What is light scattering actually? Because we were talking about it already for some time, but what does it mean? Any thoughts?
It's the way the light interacts with particles in the air. And particles are responsible for the scattering of the light. And that's why, for example, the sky is blue and during dusk dusk, the sun is lower, so the light interacts more with the particles, because like it's the path of the light is longer, so that's why the sky turns red.
Is light scattering only in the air? Because you were talking about air, of course, because on the slide. Huh?
Yeah, true. Yeah, that was one of the prime examples, but for instance, in the water as well. That's why in the sea everything looks like blue, greenish, and the deeper you get, the less red you see. Yeah.
So if we go to this this sunset here, so the sun. What's the color of light which the sun emits?
White.
Yeah, that's white. What does that mean in terms of wavelength?
All wavelengths. Yeah.
Yeah.
Like all the colors combined.
All, at least all we can see. That's fine. All wavelengths.
Yeah.
So now you say just you just said due to scattering the sunset appears red. So what happened to the blue light there on the way?
Yeah, that was a bit tricky. I think the blue light was no, the red light was mainly scattered, and the blue light was mainly sent through. But I'm not sure on that.
If that would be the case, the sunset would look exactly the other way around. Yeah.
Oh yeah. Okay. Yeah. Then I
because particles scatter blue light more efficiently than red light. So when these rays from the sun enter the atmosphere and they travel quite a long path during the sunset or the sunrise, the blue light is filtered out because it's scattered, but the red light is less efficiently scattered, and that's why the sunset appears red, while the sky appears blue because particles in the sky, although small, scatter light, and this is mainly the blue light. Yeah, very nice. And light itself, what is light?
What is light?
Yeah. What is light? I mean,
light consists of photons, and you can approach them as particles or as waves.
Yeah, that's very nice. What kind of waves?
I don't really know.
Energy? I mean, it's obviously not a water wave or a sound wave.
No.
So what is the
electromagnetic?
Electromagnetic wave. Yeah, and that then comes to the next. So it brings us to the next question. So what's the origin of light? Well, I mean, what's at the very origin? If you could zoom in on an atom, where does this light come from this atom? What happens there? Classically.
Are you hinting towards the electromagnetic effect?
No, especially to the electron. Yeah.
So the light interacts with the particle, and an electron gets in an excited state, and then it redirects. So the photon is again released, and then it's scattered in a different direction, with a different intensity.
All right, that's a very nice answer. This is an image I grabbed from Feynman lectures of physics, just visualizing this answer. So the physics of light scattering studies exactly this effect. So we have some incoming light of a certain polarization or unpolarized. And the question is how this incoming light interacts with the electron or electrons around the atom, which subsequently scatter this light. And then the question is, how is this related to the amplitude, frequency, polarization, and angle of the incident radiation? And if you know all that for a single electron or multiple or a particle, that gives you insight in many physical processes. yeah, I found this animation on the internet. It's very nice. I find this depicts an electron, and yeah, in the classical representation, when this electron accelerates, it generates light. So at the moment, it's just standing still. So you see the electric field lines here. They're just static. The further away, the lower the field strength. But now if this electron is going to accelerate, and only due to this acceleration, it generates an electromagnetic pulse. In this case, a pulse, because you will see in the movie, after the acceleration, it will move just with a constant speed upwards. There it goes. What's these field lines? I hope it's visible from your screens at home. You see this wave here, this wiggling when the electron started accelerating. That's actually the light we are studying. We want to detect. We can detect the light emitted from this electron. Here, there. And if you watch closely, it's also an interesting observation. In the direction where the electron is accelerating to, you don't see this pulse. See, so on top and on the bottom, you don't have this ripple here in the electric static or in the electric field lines. So here is where you can see propagating the light. At least the electric field component of light. Just to narrow down, because you have so many different areas which study light. There is elastic and inelastic scattering. Today we will only treat elastic scattering. This means that shown in this Jablonski diagram. This shows the energy levels of a certain atom, and for an incoming photon, it depicts what can happen. And with elastic scattering, the atom will go to a virtual energy state, and directly afterwards, it will just fall back to its ground state under the emission of a photon of the same energy of the incoming photon. So no loss of energy, etc. This is the case where we will look at today. So we don't look at any absorption, which would be the case for fluorescence. This results usually in the emission of a photon with lower energy, so a longer wavelength. And we will not look at Raman scattering, where the atom or molecule will also go to a virtual energy state, but will fall back to a vibrational state, which also causes the emission of a photon of usually longer wavelength. With Dirk, you already talked about multiple scattering. No, also today, no multiple scattering, only the interaction between light and a single particle. So single particle scattering. And then the size. Now, you have already heard that vesicles are small. Most of them even smaller than the wavelength of light, although there is a low concentration present in most body fluids which have similar sizes or diameters as the wavelength of visible light. That there are certain regimes of light scattering defined. They are defined by this formula. Alpha is pi d, the diameter of the particle, divided by lambda. And today we will mainly focus on Rayleigh scattering, where alpha is much smaller than 1, and Mie scattering, where alpha is 1. We don't look at larger particles, which could be described with geometric scattering approaches. Just a reminder about some basic optics, and perhaps something you heard last lecture from Dirk. Illumination intensity. So if you take a laser, for example, with a power of 10 milliwatts, and you focus it to an area of 100 micrometers squared, as depicted here schematically, Then the intensity, which describes how much power we have per squared area, is just a division by these two, is 0.1 milliwatt per squared area. Now, that doesn't look much, but if you imagine that you want to illuminate a whole square meter with this illumination intensity, you need already 100 megawatts. So it's a big power plant. So just by a lens and a laser, you can get actually a high energy density optically. Now, we focus the light not just in the air, but on a particle. And I've drawn here a particle in black. And I get a cross section. I get this particle exactly the same cross section as the focused laser beam. So also 100 micrometers squared. Now, if we assume that this particle scatters all the incoming light efficiently, with a scattering efficiency equal to 1, then we can calculate how much light the particle scatters. Incoming 10 milliwatt intensity of the focus, we already calculated, was 0.1 milliwatt per square micrometers. And that we multiply with the cross section of the particle, and you will see that obviously then, because the particle scatters all the light, scatters 10 milliwatt of all the light. That's quite interesting, because what you basically see is that the total energy scattered per second, so 10 milliwatt or 10 millijoules per second, divided by the incident energy per squared, so the incident energy per square meter per second, which is this I focus, which we calculated, is an area. So the sigma here is an area. And basically, by defining an area, we define the scattering properties of these particles. And this area is called the scattering cross-section. Now, in reality, and especially for biological particles, the scattering cross-section is never the real size of the particle, and it is most of the times smaller. And a more realistic picture would be this. So the area of the particle is 100 square micrometers. That's the real physical area of the particle or cross-section. But the scattering cross-section, sigma, is in this case half of this area. It's 50 micrometers squared. So there's scattering efficiency Q is we say 0.5. Now, if you do the math here, then the power which this particle scatters is the intensity in the focus times the scattering cross-section, 50 micrometers squared, is 5 milliwatt. So just by defining a quantity with the units of area, we can define fully the scattering properties of a particle, independent of the incoming laser power, which is convenient. Now, of course, the amount of light scattered by a particle is not independent of the incoming light. Even better, it scales linearly with it. So if we double the laser power from 10 milliwatt to 20 milliwatt, you will see that the power scattered by this particle also doubles. So to detect small vesicles, more intensity or more higher power laser is a good thing. Now, those were some basics. Lord Rayleigh, he actually derived a formula to predict how much light or what the scattering cross-section is of a spherical particle, as long as the particle is small compared to the wavelength of the incoming light. And here you can see the formula. Dirk already introduced this. The formula may be written a little bit differently, but it should be the same if you solve it. Scattering cross-section is some constant times the diameter to the power of 6. So that's quite a strong relationship. If you have a 10 nanometer particle and you go to 100 nanometer particles, you have a 100 times or 1 million times more light. For the rest, there is this is a division over lambda to the power of 4. So it's strongly dependent on the wavelength as well. So a shorter wavelength gives you more scattering. And it depends on the refractive index contrast of the particle, between the particle and the medium N. Now, roughly, this approximation is valid for diameters of lambda divided by 10, although lambda divided by 4 still is fine. It depends on how precise you want your theory, of course, to be. I have some examples why this goes wrong later on in this lecture. That's all. And then, in order to make some useful calculations with this formula, it's important to not only solve the Rayleigh equation, but also to take into account the optical configuration of a system. The system could, for example, be a flow cytometer. And for that, it's very important to get the textbook definitions of the spherical coordinate system. Usually this is always the same in most optical textbooks. So the light here, the illumination usually comes from the bottom, and then the illumination light propagates in the positive Z direction. The detection could, of course, be anywhere. In this case, I placed the lens in the positive Z direction. Of course, there is the X, the Y, but also the spherical coordinates. So will make me laser pointing. So hopefully you see the laser pointer now. So there is a theta. A theta runs from the positive Z to the y-axis, and then to the negative C and the negative Y, etc. Let's see. Yeah, the radius is not so important, and the phi goes from the positive X into the screen to the negative X and back. Now, to calculate how much light a particle scatters towards your lens, you have to solve this integral here. So the P as function of phi and theta, that's the phase function. So it tells you how much light is scattered in each direction, which you have to integrate then over the collection angles of this lens. Now, in this case, for this lens, I filled out the boundaries of this integral. So the theta is going from 0 to theta max. So that's from the black line here to this blue dotted line, which I made. The phi is going from 0 to 360 degrees, and that's because this lens is spherical. So we integrate phi into the screen, in the back of the screen and outside the screen. Hard to explain because, of course, the screen is in 2 dimensions only. So basically, the phi results in an extra 2 pi term here if you solve this integral. This is for a lens which is placed in the same direction as the propagating light. Now, for a flow cytometer, this is usually not the case. And the lens which we use the most is placed in the side scatter direction. And the main reason is that this is perfect dark field, which means that any light from the laser has difficulty entering the lens, such that the background on the detector is very low, such that we can detect smaller particles. Now, in this case, of course, the boundaries of the integral, they change. The theta goes from theta minus to theta maximum, as depicted here in blue. So this is 0. This is, it's up to you to measure it, probably a degree or 70, and this is a degree of perhaps 120. Phi, I did not draw in this image because very hard to draw but it would in this case be similar to theta. Yeah, the slides are on Canvas, so you can check, you can download these slides as a reminder. Because I'm scrolling now further to the next assignment. It's a little bit larger assignment than the previous one. And the question is, how small can we get with flow cytometry in terms of vesicle detection? And yeah, for that you have to solve this equation here, this integral, where I defined a phase function here, P as function of theta and phi. Yeah, the scattering cross-section is just given by the Rayleigh equation, which you can solve using all the parameters written here. So in this case, this is a flow cytometer with a beam intensity in the focus of 1,000,000 watt per square meter, wavelength 405 nanometer, the refractive index of water and vesicle are defined. And for another question of a COVID virus particle, the numerical aperture of the microscope objective, and the lower detection limit, which is the smallest power which the detector can still detect in order to sense a particle. Now, the configuration of the flow cytometer is shown as here. So just similarly to the spherical coordinate system, which we just discussed, the illumination comes from the bottom here in the positive z direction. The particle flows in a flow channel, and once it's in the center here, it's illuminated by this laser beam. It scatters light, and it scatters light to the detector, which is here depicted in green. The detection angles are given by the numerical aperture. So this beta here in the formula for numerical aperture is equal to the beta there. And that would be sufficient to define the angles, the boundaries of the integral for theta and phi. The questions are as follows. First question, what is the power at the detector of the flow cytometer for a vesicle with a diameter of 100 nanometer and 200 nanometer? For that you can solve these equations with these properties. And the most important thing is to define the right boundaries of these integrals. Then the question, can you detect 100 nanometer and 200 nanometer vesicles? Now, in order to judge whether you can detect those or not, you have to compare the measured or the collected signal intensities to the lower detection limit. Then the question is, what is the smallest vesicle that can be detected? And what's the smallest COVID variant that can be detected? And yeah, for a vesicle, the refractive index is 1.40. For a COVID virus, 1.50. You can probably already predict which particle is easier to detect. And then the final question, what is your opinion about the use of flow cytometry to detect vesicles and variants? All right. I don't know whether you would prefer this or this on the screen. It's time to start the assignment. I suggest to at least take 40 minutes for that. So let's meet at 5 to 4. I stay here just to answer questions. So if you have questions in between, please let me know.
Yep, so am I. I'm going to stop the recording for this session, so